So today we're going to look at parametric and inverse relations. Parametric and inverse. All right. So some functions have an x and a y, and then they also have time involved. Okay? So you can have something traveling in an x direction and y direction with respect to time, and then when you add time in, it's kind of like a third variable, which makes kind of a parametric equation. So you'll see that in a little bit. And other functions, we have to talk about inverses of functions. All right. So another way to define functions is to define both elements, x and y, in terms of another variable called t, which is a parameter. Okay, so in this equation, our sample, x is equal to t minus 1, y is equal to t squared minus 2, or t squared plus 2. So if you're told to find t equals negative 3, negative 2, and so on, the ordered pair for negative 3, you stick negative 3 in for t, and you get negative 3 minus 1, which is negative 4, and negative 3 squared, which is 9, plus 2, which is 11. So our first ordered pair would be negative 4, 11. So at time equals negative 3, our first order pair is negative 4, 11. At time equals negative 2, we're at negative 3, and then 2 squared is 4, plus 2 is 6, and so on. Yada, yada, yada. You get that? Yes. We're good? All right. So here are all the ordered pairs that are created from that last one. Okay? All right. Is y a function of x in this parametric equation? So we can take y equals t squared plus 2, and then since t is equal to x, let's see, what was it? No, x was equal to t minus 1, right? Then we can replace the t with x plus 1. You can solve for t, stick that into y, and here's what y equals. Okay? So y would be a function of x. It would actually be a parabola. Okay? So if you are told to find a function for that, then you just solve for t for the x part and plug it into y. Okay, in inverse relation, y equals x squared and y equals the square root of x are inverse relations. Y equals x squared is a relation. Whoa. Gotta go back, Mr. Bierschbach. Is a relation that looks like this. Y equals the square root of x is a relation that looks like this. Okay? Now, here's the tricky part. The domains are really, really important for this. Okay? Because here we have two lines. One going this way, one going this way. Here we only have one. Okay? Because if I went like this, would it be a function? No, because it doesn't pass the vertical line test. Okay? So the square root of x has a limited domain from, and then I did it again. I moved the wrong way because of how I use my cursor. It goes from 0 to infinity. So if we're talking about inverses, this only has an inverse from 0, and I did it again, from 0 to infinity. Okay? That's only where it has an inverse. This is a function wherever, but only the 0 to infinity part has an inverse. Okay? All right. Let's continue on to the next slide. Okay? So to figure out if a function has an inverse through its whole domain, whether it's a one-to-one function, we use what's called the horizontal line test. If we have a horizontal line and it hits it twice, it is not one-to-one. Okay? Now, if we take and limit the domain of x squared to 0 to infinity, then it passes a horizontal line test. Then it is a one-to-one function where it does have an inverse. Every one of these points has an inverse. Okay? Let's look at y equals x cubed. Y equals x cubed is a function that looks like this. Is it a one-to-one function? Yes, because no matter where we draw a horizontal line, it passes the horizontal line test. Okay? So this one is one-to-one. Every point is a one-to-one function. In x squared, you have to limit the domain before it becomes a one-to-one function, before we can find its inverse. Okay? So an inverse function, we say f of negative 1 when we're finding inverse functions. Okay? If we have a function that can have an inverse, then its inverse is f of negative 1. We will show you that on the next slide. So how do we find the inverse for this function? Well, what we do is f of x is really just like y, correct? So in other words, I'm saying y equals 2 over x minus 1. Okay? When I want to find an inverse, 2x over x minus 1, I switch around the x and the y. So I say x equals 2y over y minus 1. And then I'm going to solve for y. So when you want to find an inverse, you switch x and y around, and you solve for the y. What's my first step to get y alone? Doesn't look that easy, does it? I'm going to have to multiply both sides by y minus 1. So y minus 1 times x equals 2y. Okay? Then I'm going to divide by y on this side, both sides, and divide by x on both sides. So the x's cancel on this side and the y's cancel on this side. So y minus 1 over y equals 2 over x. And then I have to somehow get y alone. How did they do it? Multiplied, distributed. Ah, Mr. Bierschbach, you're so stupid. Can't divide. I knew something didn't look right there. Distribute. xy minus x equals 2y. There we go. Now we got to get our y's together. So I'm going to subtract 2y from each side. Add x to each side. Factor out a y. And then divide by x minus 2. So y equals x over x minus 2. So the inverse of my function equals x over x minus 2. Now, there is restrictions on the domain for this. There's a couple restrictions. What's the restriction created by this one? X cannot be what? X cannot equal 1. What's the restriction created by this one? X cannot equal 2. So those are 2 points where we have restricted domains. All right, so this is their way of solving it, which basically was my way. All right, the reflection principle. Everything on the inverses reflect around the line x equals y. So here's a function that we want to find the inverse. The line x equals y goes like this. And if we reflect around that, okay, this point goes to here. This point here goes to about right here. This point here goes to about right here. This point here crosses. This point here is about right here. So what happens is it kind of looks like that, and it crosses like that. See how they're mirror images of each other across that line. Okay, so let's say we have a function, and I'm going to go on to a different page here because they're going to show, yep, you draw the line and you flip it across, and that's what it looks like. So let's say we have a function, y equals 2x plus 3. What does that look like on the graph? Well, I have the point 0, 3, right? And the point 1, 1 what? If we stick a 1 in here, we get 5, and 2, 7. Okay? Now, if I want to find the inverse of this function, I switch the x and y around. X equals 2y plus 3. So to get y alone, I subtract 3 and divide by 2. So the inverse of this function equals x minus 3 over 2. Now, what's interesting about this is, what if I put in a 3? What am I going to get? 3 minus 3 is? 0 divided by 2 is? What if I put in a 5? What do I get? 5 minus 3 is 2. 2 divided by 2 is 1. What if I put in a 7? Notice the relationship between these. What happened? Just switch around the x and the y. So 3, 0, 0, 3, 1, 5, 2, 7. The original function looked like this. The inverse to that function looks like that. Crosses this line. Okay. All right. Are these inverses of each other? Well, if we go f of g of x, let's see what we get. F of g of x means we're going to take the cube root of x minus 2, the g function we're going to put into the f function. We're going to cube that, and we're going to add 2 to it. Well, when you cube a cube root, what are you going to get? What's underneath? What's x minus 2 plus 2? X. Let's find g of f of x now. So we're taking the cube root of x cubed plus 2 minus 2. What's x cubed plus 2 minus 2? X cubed. What's cube root of x cubed? X. If both your functions give you an x in the end, they are inverses of each other. If both your functions lead you to an x, they're inverses of each other. Okay? All right. So find a function algebraically. We flip-flop the x and y and solve for x, and we say f inverse is equal to that. And then we can figure out if the g function and the f function are composite functions. If they are and they both lead to x, they're inverses of each other.